Hey everyone, and welcome to today's Explainer. We are about to uncover the hidden mechanics of our planet. We're going to explore exactly how solid rock transforms deep underground in some of the absolute most extreme conditions you could possibly imagine.
To kick things off, we've got to ask a pretty fundamental question. How exactly does solid rock morph into an entirely new structure without ever becoming molten magma? Like it never melts. It's a process called metamorphism, and it is happening right now, kilometers beneath our feet. So, here's our agenda for today. We're going to start by exploring Earth's metamorphic engine. Then we'll see how it's forging new textures, measure metamorphic grades, and finally, look at extreme environments. All right, Section 1, Earth's metamorphic engine, analyzing heat, pressure, and fluids. Let's get into it. There are three primary agents driving this massive planetary engine. First up is intense heat. We're talking 200 to 1100 degrees Celsius. This heat actually vibrates atoms so vigorously that they just jump, literally jump, to new positions within their solid crystal lattice. Wild, right? Then we've got crushing pressures. This ranges from a relatively low 3,000 bars to a staggering 50,000 bars, pushing down 15 to 35 kilometers below the surface. To put that into perspective, that is a whole lot of weight on top of you. Finally, chemically reactive fluids, mostly water and carbon dioxide, get in there. They actively participate in chemical reactions, swapping out atomic elements in a process we call hydrothermal alteration. Now, what's really fascinating here is the stark contrast in how pressure actually applies itself. You have confining pressure, which crushes equally from all sides. This effectively shifts the chemical equilibrium and sparks the chemical reactions needed to form new minerals. But then you have directed stress. This is generated by tectonic plates smashing together, causing unequal force that pinches and pushes unevenly. Basically, it mechanically deforms the rock. Moving right along to Section 2, forging new textures, structural simulation. The crucial mechanism to grasp here is recrystallization. This is a process where atomic structures dissolve from areas experiencing really high stress, and then they precipitate or regrow in areas with lower stress. They literally regrow larger. Think of it kind of like adjacent soap bubbles coalescing into a single bigger bubble. Or honestly, like solid rock stretching and deforming exactly like silly putty, all without ever actually fracturing. These mechanical changes give us huge, massive clues for understanding how deep underground faults actually move. And, well, when we apply that directed stress we were just talking about, we get foliation. Under this uneven pressure, platy minerals, especially the mica group, are forced to line up perfectly perpendicular to the stress. They stack together tightly, just like the pages in a book, creating a highly organized planar fabric. It is essentially the geological equivalent of electromagnetic wave polarization. Conversely, when rocks are subjected to intense heat and equal confining pressure, so missing that directed, uneven stress, they form non-foliated textures. Instead of lining up in neat little planes, they form an interlocking grid of crystals that just grow in all directions. A perfect example of this is a porous sandstone fusing into a highly durable, ultra-hard quartzite, or limestone recrystallizing into that beautiful interlocking marble we use for countertops and statues. Okay, Section 3, Metamorphic Grades. The Barrovian Sequence, Data Grid. The Barrovian sequence, which, by the way, was mapped out by British geologist George Barrow back in the late 1800s, brilliantly illustrates how a simple sedimentary rock, like shale, transforms progressively as heat and pressure dial up. We start down at the low grade with slate, move up through phyllite and schist, and finally reach high-grade gneiss. And what's incredibly useful for geologists here are those index minerals. Finding a specific mineral, say chlorite or garnet, instantly tells us exactly what temperature and pressure conditions that rock was forged in. It's like finding a built-in thermometer and barometer, allowing geologists to map out ancient, completely eroded mountain ranges. Tracking a single rock sample as pressure increases through these grades is just visually stunning. First, microscopic clays flatten perfectly to give slate its distinct flat cleavage. Then in step 2, as temperatures rise, the grains grow slightly larger, giving phyllite this really unique, wavy sheen. By step 3, the platy crystals are large and clearly visible, creating the scaly texture of schist. Finally, at the absolute highest grade, the rock gets so hot it's right on the verge of melting, forcing the silicates to separate into those stark, beautiful black and white bands you see in gneiss. And that brings us to Section 4, Extreme Environments, Localized Anomalies. So, we have two incredibly common, yet completely distinct metamorphic environments. First up is contact metamorphism. This happens when hot magma physically intrudes into existing rock. It bakes the surrounding rock like a giant subterranean kiln. So you get high heat but low pressure. This creates distinct rings of altered rock called areolas, forming hard, dense rocks like hornfels. Then we have regional metamorphism. This is the whole shebang. Metamorphism on a massive scale, where converging tectonic plates crush vast areas of the crust, ultimately building towering mountain ranges.
But things get really wild deep in subduction zones. When cold oceanic crust plunges downward into the mantle, it creates a very rare geological anomaly, extremely high pressure but relatively low temperatures. Why? Because that plunging crust is still cold. This unique environment forges a striking blue rock called blue schist, getting its color from the index mineral glaucophane. If it sinks even deeper into the earth, the immense pressure transforms it into an incredibly dense rock called eclogite.
Then we have the localized, intense violence of fault metamorphism. Right along active tectonic faults, the sheer grinding force dynamically recrystallizes pulverized rock, literally called rock flour, into banded rocks called mylanites. What I love about this is that larger, stronger crystals, like quartz or feldspar, get caught in the shear force and they're just smeared out. This traps these striking, asymmetrical, eye-shaped crystals known as augins right within the rock matrix.
And finally, we have shock metamorphism. Now, this isn't caused by slow plate tectonics. No, this is triggered by violent meteor impacts. A bolide impact vaporizes and fractures the crust in absolute milliseconds. The extreme rapid pressure creates entirely new structures, distinct branching horsetail fracture patterns called shatter cones, unique polymorphs like shocked quartz, and it even ejects gravel-sized droplets of melted, non-volcanic glass known as tektites, literally raining glass.
As we wrap up our explainer today, I want to leave you with this pretty provocative thought. Knowing that these massive, mostly unseen geological forces, immense heat, crushing pressure, reactive fluids, are constantly at work deep in the crust, rewriting the very atomic structure of the planet, what do you think the rocks beneath your own feet are slowly transforming into right now? Keep observing, keep questioning, and I'll catch you in the next explainer.